So last time I started discussing the algebra cohomology, and I said to you that by reasons which you can call personal, I actually wrote much more in my notes than I will be able to discuss here. So if you are in the lucky event that you are interested, you can look through it. But there are several exercises, and I'm not going to discuss the solution here. It's very pleasant to think of it. But very briefly, I will observe at least the most interesting of this exercise. My goal actually is to convince you, if I am able to, that real algebraic cohomology is actually an interesting and important thing. And this thing, the algebraic cohomology, arises in some very natural algebraic problems. From a more advanced point of view, this is actually some way to convince people who have doubts that the real algebraic cohomology is maybe interesting, but not the way to observe their real importance. Because, these direct algebraic applications, which I'm going briefly to observe now, they are related to the cohomology HQ. Q is called dimension of the topological terminology. For Q equal to 0, 1, and 2, and a little bit of 3, which I will not touch today here, but it is written in my exercises. In reality, certainly the cohomology of real algebra is interesting and important in higher dimensions, where it is related to various theories of characteristic classes. This is something which I will not touch at all. I just mention it to create sort of right impression. So the definition, which I repeat, is the following. We have a real algebra G over some field of characteristic 0. Now I consider NV is a representation of G. I can say that everything is finite dimensional, but in reality it is not necessarily so. Now CQ of G semicolon, we also called the space of cochains of G with coefficients or values in V. When I do not write over what, I mean home over the ground field, just linear maps. Which can be described as Q linear schizometric forms on G with values in G. You understand? Just functions of Q variables. Variables are elements of G. The function is Q-symmetric with respect to the arguments, and the values belong to G. No representation so far is involved, but there is a special map differential which raises the dimension by 1, and which is defined by a certain formula, which I... So if C belongs to CQ, then delta C belongs to Q plus 1, so the function of Q plus 1 variables, and there is a certain formula, which I repeat here. formula is here. I believe that it is correct. And if you have immediate questions, the only question which I'm not going to answer, although I said something last time, is the question why. Now, this formula, on the first glance, may seem sort of long and complicated, but actually, in some sense, it's very natural and actually classical. This formula was, I believe, in textbooks in analysis more than a century ago, in slightly different context. Then it is called the Cartan formula for the differential forms. The fact, the crucial fact, which actually is the base of the whole theory, is that if you repeat this operation twice, then you get 0. By this reason, the image of delta q minus 1 is contained in kernel of delta q. These two spaces have special names and notations. These elements of this space are called cocycles, as in topology. And the space has maybe not well justified notation, ZQ. Z is because of German word cycle, but it's cosine. So, and this and then the quotient also vector space is known as HQ GV, and it's called the space of Q-dimensional Qth cohomology of G with the coefficients in V. I do not check the main formula, delta q minus 1 is equal to 0. Although it is checked directly, all we use is Q commutativity of the forms plus the Jacobi identity, nothing else. And well, we don't have anything else, so what can we do? And then, so I do not do it. But since I'm going now to concentrate my attention to maybe not the most interesting, but still important case of cohomology of small dimension, very much in the spirit of this. Yes, Dale.
I have a question about the formula.
Formula, yes.
So in the second line, you're multiplying.
No, I apply.
Yep.
C of all this stuff is an element of V. V is a space of representation.
Oh, so it's not from G to V yet.
I apply the whole map. Take values in V. This is in V, and then I apply this element of G.
So that's you're using the.
I use my representation. Yes. Good question. I should have say this. No. Well, I hope that I will deal somehow with the existing amount of chalk. It is not very clear. No hope. Good. Then
I'm sure that white box has chalk in it.
There's chalk line.
Maybe. Where?
On the
Here.
right one, yeah.
You sure? Wonderful. Yes, I will use it. Maybe. Thank you. Should be white, yes. That's chalk. What I'm going to say now, in addition to what I said, is the following. The differentials delta q with q equal to 0, 1, and 2. This formula becomes very simple. So C 0 QV GV. Maybe it requires additional explanation because it is a function without arguments but with domain. This is simply V. And delta 0, we take an element of V, which is actually belongs to C0. Apply delta to it. This will be a function of one variable. And this minus GV follows from this formula. Very simple. Now, C1 into C2. So we have a function of one variable, right? With values in V. And C. And this is C of G1 G2 minus G1 of C of G2 plus G2 C of G1. For if you are interested in that, I will also write on the bottom, also I have probably enough space for this, the explicit, oh, this is delta 1, this is delta 2. So C is the element of this. Then I have delta C of three variables, G1, G2, G3. I write, it is C of G1, G2, G3, and then I add two more terms, which are obtained from this by cyclic permutations of G1, G2, and G3. You understand? So three terms, then with C of G2, G3, comma G1, and so on. Minus G1, C, G3, and again two terms obtained by cyclic permutations from this. So six terms. Not precisely this, some permutations here, if you compare this with this formula, but actually the same. Yes. Now, I do not remember, and I don't want to remember how many exercises regarding the low-dimensional cohomology is given in my notes, but I want to discuss two actually, because the first one does not deserve any discussion. Maybe it is an exercise I don't remember. But let us look. Let us look. H0. H0. So we have kernel of delta 0. And we will factorize it over image of delta negative 1. Actually, delta negative 1 maybe is not described there, but certainly it is 0 by definition. So what is kernel of this? This contains all those elements V of V, for which this is 0 for all G's, right? These things are called invariants. So the space Z0, space of cocycles, is space of invariants, and we factorize this over nothing. Nothing is nothing. So the zero-dimensional cohomology is simply the space of invariants. It is very common, not only for actually the notion of cohomology is very broad in mathematics, and this is just one of many examples. H0 is always some sort of invariance, whatever you consider. Now, I want to consider three more things, very briefly. H1. When I say briefly, I mean that I will say that this is cocycle, this is coboundary, but I will never check this. It is my exercise. So what is C1 of G? For the coefficients, I take G again. And this is a joint representation. What is an element of this? This is a linear map of G into G. Now there is some formula. So this map, C, cycle, it means it belongs to Z. Boundary means that it belongs to B, the image of the differential. Do you have an idea what these two things are? So all of them, every C is a linear map of G into G. And it is cycle if and only if there are two ways to answer the question. Either to look at the definition or just think what could it be after all. Dale, you want to say something?
Is it in the center?
The center. Center belongs to G. This is a map of G into G. A homomorphism of G into G. How a homomorphism may be in the center?
I think that's
No, it's not related to the center. Are there any linear maps of G into G which sort of distinguished, have name? Yes, there are. What are they, Paige? Yes, say, please say.
I don't know.
Do you know?
Like, I don't know.
You know, certainly know. Don't want to say. You want to check whether I know it. But believe me, I know. So these are derivations. Cycles are derivations. Now, boundaries. Boundaries, first of all, boundary of what? Of an element of G, right? Element C0, which is an element of G. Some special derivations which depend on an element of G. What are they? Inner derivations. So when we compute the homology, we factorize. Space of all derivations over the space of inner derivations. Sometimes the elements of this quotient are called outer derivations. So H1GG is the space of outer derivations. If it is 0, then every derivation is inner. If the algebra G is not commutative, there are inner derivations, not zero derivations. You can say no derivations at all. There are derivations, but some derivations are sort of, how to say, you need to use some word which, so they're not very interesting, but still we don't want to say that they're not important. Some derivations are sort of simple, sort of trivial, sort of visible, inner derivations, but there may be other derivations. And then there arises a quotient. This is one-dimensional homology. This is example number 1. Number 2. There is such a thing in algebra, in particular for fully algebras, as a central extension. A central extension is the following. We have a Lie algebra G, is a Lie algebra. Then we create a new Lie algebra, which has, I write C actually, field is arbitrary, which has a central one-dimensional ideal is the central. One dimension C. And then factorize, you get G. So G tilde is obtained, has dimension 1 more than G. And actually, G is the quotient of this thing over the central one-dimensional ideal. This is called central extension. There are many examples. We will discuss some. Now, if we have G, how to describe all central extensions? First, to describe all central extensions or whatever, we need to have some equivalence relation. Otherwise, we don't know what to describe. So, two central extensions are equivalent if there is an isomorphism which actually makes the whole diagram involving the two identity maps commutative. So sometimes two central extensions may seem different actually are the same in some sense, because there exists an isomorphism between the extended algebras which respects the whole structure. That is, this embedding of C of one-dimensional center. Not just the isomorphism between centers. C is seats. That is, we have an isomorphism between C, between a copy of the ground field and this central ideal. Do you understand the definition? Now, this is a very natural algebraic problem, which has, however, a very direct cosmological description. Look. Suppose we have a central extension. Then, as a vector space, this is the direct sum of G and C. It is even not important that it is the direct sum. What is important that there are two vector spaces and this projection, which is the algebra homomorphism. Suppose that, so this, let this be P. And this simply I regard as an embedding. Suppose that we fix some inverse map so that if you repeat it twice, so first take this and then back, you get the identity. But this probably is not a Lie algebra homomorphism. If it is, then utility becomes as a Lie algebra, the direct sum of this and this, sort of very much trivial extension, not interesting. If it is not a Lie algebra homomorphism, then we can consider how much this is violated. Take two elements, G1 and G2 in G, take the commutator and apply Q to this. And we would like that it is like or don't like, that it is equal to the commutator. We should compare this. To compare two things, it is very natural to take the difference. I get a function. Now, the values of this are where? Certainly in G tilde. But if you apply P to this, you get 0. Because PQ is the identity. So this belongs to the kernel of P. That is to C. And we get a C valued. We get a C valued function, C of G1 GQ. Now I don't want to provide details. First, this can be regarded as a cochain of the Lie algebra G with the coefficients in C. This cochain is a cocycle. This follows from the fact that G tilde possesses the Jacobi identity. Very easy to derive from this. I'm not doing that. So as soon as we have a central extension and this Q, we have a cocycle in Z2 of G, C, right? But Q, we have an arbitrary choice over Q. And then the next thing, which I'm again not going to provide details, that if you replace Q by any other map with PQ is the identity, you actually affect this C by adding a coboundary to it. This is something which you should check when you do the problem, but the fact is that the space of all, the set of all one-dimensional central extensions of G has a one-to-one bijective correspondence with H2 of G with the coefficients in C. By the way, when physicists speak of cocycles, usually they mean this. For physicists, a cycle is this thing. They take a cycle. And central extensions in physics are very important. Actually, in reality, semi-simple finite dimensional Lie algebras never have central extensions. Non-trivial. And in the infinite dimensional case, it's very much not so. So for physicists, central extensions are important. I could say a lot about it, but I will not do this. So second example is two-dimensional homology of G with the coefficients in C in the ground field. Is precisely the set of central extensions. I said central extensions. Maybe you should be surprised by the fact that we speak of a set of central extension and H2, which is a vector space. So the set of central extensions somehow, this instance with correspondence, also becomes a vector space. In particular, you can add to central extensions. How to do it? No, I will not discuss it, but it is very much understandable. The last example is the following. Again, I begin with a very natural algebraic problem. I say algebraic, it's not precisely algebraic. At least I will not formulate it as an algebraic problem. Suppose that you have a Lie algebra. What is a Lie algebra after all? It's a vector space with some commutator, right? Which satisfies some axioms. Suppose that we want, without changing our vector space, we want somehow to change the commutator continuously, smoothly, analytically, algebraically, formally. Well, this is infinite. So I want to define a new commutator. So when t is 0, it is my old commutator. And when t varies, this varies, certainly, it should still satisfy all the axioms, skew commutativity and Jacobi identity. This is deformation. There are many examples. Let us try, as a function of t, to present it as a power series, but I will stop immediately. Some function alpha of g1, g2, plus subsequent terms, which I do not specify now. Okay? So such a thing which actually is given as a function of t up to the term of degree 2 or more. Then, next thing. First of all, this alpha is a function of two variables, g1 and g2, with values in g, right? Skew commutative, because my commutator should be skew commutative, this also should be skew commutative. So this alpha is actually is a chain. Right? Suppose that we are interested only in this alpha. This means what? That we take this expression and check the Jacobi identity, but we do everything, including the Jacobi identity, modulo t squared. So I write for this commutator, I write the expression which should be 0 by the Jacobi identity. But I always ignore the terms which contain t squared or more. If I do this, then this alpha is called, expectably, an infinitesimal deformation of the Lie algebra. I consider this deformation only modular terms of the degree t squared. And this alpha becomes a two-dimensional cochain. Now first, it is a cocycle. This is equivalent to the Jacobi identity for the new commutator. Moreover, sometimes, actually, the deformation should be regarded as trivial. This is in the following case. Suppose that we don't have any deformation of the commutator, but rather we have the deformation of G itself. So what do we have? A deformation of the identity homomorphism of G. Phi0 is the identity, and then we define a new commutator in the following way. We apply phi t to G1 and G2, take the usual commutator, and then back. When t is close to 0, this is an isomorphism, so we can take the inverse. So actually this means that we do not change the commutator, we rather change, if we wish, the coordinates in G. Just deform G. Such deformation should be called trivial, or two deformations are equivalent if one of them is obtained from the other one as a combination with a trivial deformation. You understand? So, alpha is a cocycle, infinitesimal deformation. Two infinitesimal deformations are, well, very long word, excuse me, infinitesimally equivalent if and only if the corresponding cocycles are cohomological. So if their difference is a coboundary. This gives you a seemingly very nice description of all infinitesimal deformations. Infinitesimal deformations up to a very natural equivalence of a Lie algebra is the same as the two-dimensional cohomology of this Lie algebra with the coefficients in the adjoint representation. I stop here, or almost stop here. Before doing that, I want to make my last remark. Because I know that if I don't say this, somebody is going to ask. So, answering a question which was not asked, I say, suppose that we have an infinitesimal deformation. But who cares about infinitesimal deformation? We want to have some real deformation. Is it possible to extend it, say, to the terms with t squared? In such a way that still the Jacobi identity holds. Then t cube, and so on. Actually, there exists an abstraction to it. If we have an element of two-dimensional cohomology of G with coefficient in G, this is an infinitesimal deformation. It is not necessarily true that it's extendable to the deformation involving t squared. For this, a certain three-dimensional class should be equal to 0. I included the description of this class in my notes, so you can see it there. Then the story is endless. The story is endless. Actually, the end still not reached. Because then after t squared, we want to know about t cube, t to the power 4, and so on. There is actually a chain of abstractions. At every step, we need to do something involving three-dimensional homology of G with the coefficients adjoint representation. And if at every step, if we are this lucky, and at every step we have this continuation, and we forget to ask how many different continuations it has, this question is actually very tricky. But if we have this for every t, then there arises a question where algebra fails to do anything. It is a question from analysis. We will get a series. And series, as you know, if you ever heard about that, there are convergent and divergent series. And the series which we get, a formal deformation, can be easily divergent. And in this case, as far as I know, algebra has no answers to this. There are theorems in algebra, like Artin theorem, but as far as I know, this question remains unanswered. There are formal, very natural formal deformations of Lie algebras, actually infinite dimensional, which actually are divergent, and no algebra sees this. Formal deformation, yes. Converging deformation, analytic deformation, no. Here I stop. Any question? No, I don't stop. I have 15 minutes. And I say I stop. I don't mean that I leave the room. But I mean that I am going to answer your questions. Your question. Call it Dale. Introduce. Question. Yes, I thank you. No? Page, my last hope. Yes, thank you. Yes.
Trivial central extension will be like extension of G over G prime. Like G is a trivial central extension of G over G prime. No, sorry.
Zero G prime. What is G prime? Well, we can just, when you formulate a question in such a way that I am able to understand, I will try to answer. Good. So this, again, this, by the theory of deformations, is something which contains very interesting questions. All these questions actually, in reality, arise only when the algebra is infinite dimensional, at least not semi-simple. In the semi-simple case, everything is zero, which you consider. I will mention it if I have time. If I don't have time, I will mention it next time, on Wednesday. Yes. Now let me return to the general theory. Maybe it is better than turning to the general theory to say something about our case, semi-simple Lie algebras. Imagine that G is semi-simple and V is finite dimensional and V is finite dimensional. Then some things are true. The proofs are not very complicated, but they not the proofs, the statements involve some topology. And by this reason, I will not speak of it any seriously here. So first, if G is semi-simple, finite dimensional semi-simple Lie algebra over any field, it may be complex, but not necessarily. V is representation. Then first of all, so rho G into GLV. There is a space V rho, space of invariance, which is embedded into V as a subspace, actually sub-representation. It is very clear that if we have a representation, sub-representation, there is also embedding for cochains, cocycles, everything. So we have a map for any Q this into this. So far nothing, but now something. This map is an isomorphism. It is one of those theorems which are so deep and interesting that it seems unfair that the proof is so simple. I will not give the proof, even not discuss it, but the key word is Casimir operator. What does it mean? First of all, if V is irreducible and don't have invariance, then V rho is zero. Zero gives zero. The homology with the coefficient 0 is 0. So first of all, we see that the homology of a Lie algebra in a representation which do not have invariance, for example, irreducible. I don't mean one-dimensional representation. So non-trivial irreducible. The homology is 0. And this is a very strong statement. Second, if we consider a representation with invariance, this means that we consider what is V rho? V rho is a direct sum of several copies of C. C is trivial representation of G. So to know this, we need to know this. And again, this thing is fully known. I will formulate, so now I consider the real case. Let G be a real Lie algebra. If G is a Lie group, Lie algebra of some group G, and G is compact, then this is the same as the usual homology, if you know what it is, but you can consider it Ram homology or singular homology, any homology theory which you may know, that actually this is a purely topological object. If G is a Lie algebra, some Lie group, but this group is not compact, then there is a trick which I'm going to discuss here in the very end of this course. You know, for any semi-simple Lie group, semi-simple means that Lie algebra is semi-simple, compact or not, there exists a thing which is called the compact form. Another Lie group of the same dimension, and these two Lie groups have the same complexification. From the point of view of homology theory, complexification is nothing. Then you complexify Lie algebra, its homology also complexified. Same dimension, same everything. So this means, roughly speaking, that G and G prime, G bar have the same homology with trivial coefficients. So if you have a Lie group, not semi-simple and not compact. Like, yes, you're right. Like SL2, SL3, SLNR. Then you should find another Lie group of the same dimension whose Lie algebras are related by this. In the case of SLN, it is UN. In the case of SLN, no, SUN, it is SUN. In the case of GLNC, it is the product of two copies of UN. And many SUN, many other examples. What is important here is that topology gives us some hints. You know, a semi-simple, simple, for example, Lie group never, topologically, it has homology like a product of spheres, of odd-dimensional spheres, and never S1. This is some complicated topological, well, complicated, not very complicated topological result, but I want to say that never ever simple Lie, non-commutative Lie groups have homology of dimension 1 and 2. 3 is the first dimension where the homology may arise. Like SU2. Topology is a three-dimensional sphere. No homology dimension 1 and 2. This is the topological result, and I'm not going to discuss it anymore. What I am going to discuss is the following thing. Actually, if you translate this into the language of Lie algebras, then you have the following fact. Again, I keep this. If G is semi-simple, any field, V is representation. Everything is fine dimensional, is written here, but we always remember this. Then H1 and H2 is always 0. And this is called Wheaton's lemma. What can I say about this? If we look at our previous constructions, we can deduce from this that semi-simple Lie algebras do not have central extensions, non-trivial, do not have outer derivations, do not have deformation, infinitesimal deformations at all. Right? This is a very interesting circumstance. Moreover, there are other problems. Related to semi-simple Lie algebras, which can be resolved in a purely cohomological way using H1 and H2. For example, Weyls' theorem, I mentioned it. I will prove it next time. At zero cost. Every finite dimensional representation of a semi-simple Lie algebra is a direct sum of irreducible representations. How on the earth should this could be proven? Take a representation. If it is irreducible, we have nothing to do. If it is reducible, it has a subrepresentation. V is represented, W is a subrepresentation. What we want? We want to find a complementary representation. A representation Z or whatever says that, so another subrepresentation of V says that V is direct sum of these two representations. You understand? And a cohomological question very much related to the question, very much similar to the question which we considered, arises. Certainly in V we can find a subspace which is complementary to W, right? That is, we have a linear map of the quotient V over W as a representation into V, right? Which, however, is not maybe a representation homomorphic. It does not respect, doesn't commute with the representation operators. So for every element of the Lie algebra, there arises something. We write precisely what arises, and we see that there arises a one-dimensional chain with some coefficients. These coefficients are described, and then we see that actually this map of V factorized over W into V is not unique. We can deform it. And precisely this deformation, the existence of the deformation arises that a certain cocycle is a coboundary. If you know that H1 is 0, it is a coboundary. There are several pure algebraic theorems regarding Lie algebras which follow from the Witness lemma. Now I have 1 more minute, so I sort of finish. So I will not, my notes contain full proofs of all the things. I will prove here only that H1 is 0. And I will deduce from this the fact that every representation of a semi-simple Lie algebra is decomposable into the sum of irreducible representations, which will be important for me. This will follow more or less immediately from the fact which we deduced from using the Casimir operator, if you remember, that if V is a representation, then V is the direct sum of V super row plus V sub row, if you remember the annotations. Precisely this we need and nothing else. So this will be done next time. I hope not to spend too much time for this. However, my schedule. So next time I will give you this test. I hope you will enjoy it. Whoever comes, including the people who are not registered, I will look through your, well, I will do whatever is needed with the tests. Tomorrow at 3:30, but Indrajit is going to come at 4, so at least at 4. I will be in my office answering questions if you have them. On Friday, this is the test. On Monday, we have a holiday, right? Then next lecture in reality is a week from now. Wednesday, I don't remember the precise date. Thank you for your patience.